Okay, perfect. Yeah, my name is Tobias Friedetzki. I'm from the University of Würzburg and located at the Department Center for Artificial Intelligence and Data Science. And our team developed iMedSTAM. It's a foundational model for interactive segmentation and tracking anything in 3D medical images and videos. Um, yeah. And basically, we use the EfficientTem architecture, which is a more lightweight version of the popular SAM2 model that can segment any objects in videos. And for 3D images, we first slice the volume along its third dimension and then process these 2D slices sequentially. A lightweight image encoder first extracts the features from the current slice, and to capture those 3D dimensional spatial relationships, these image embeddings are then cross-attended to memory representations from previous slices. After that, the mask decoder incorporates the user input prompts and predicts the segmentation masks for the current slice. Finally, a memory encoder transforms the prediction and image embeddings and stores them in a memory bank for subsequent slices. The improved efficiency of EfficientTem results from replacing the higher image encoder we have in SAM2 with a more lightweight, non-hierarchical vision transformer, and from using a more efficient memory module that approximates the spatial memory tokens by applying pooling to the spatial embeddings of the memory bank. Obviously, this gives us a performance hit, but given that interactive segmentation requires online inference with a reasonably fast user feedback, this was a trade-off that was acceptable in our eyes. For this approach to truly work with 3D images, we adapt the inference pipeline of EfficientTem and propagate the initial box or point prompt of the middle slice bidirectionally, so to speak, from the middle to bottom and from bottom to top. So the resulting 2D segmentation masks are then reassembled into a 3D mask, which represents our final prediction. Yeah, and for the selection of the 10% core set, we aim to replicate the modality distribution of the validation set and also try to always select at least one sample from the sub-data sets in order to have as much variability as possible during the training. So the training of our model is pretty straightforward. We use random affine transformations and horizontal flips for data augmentation. And for the interactive part, we try to simulate up to 3 refinement clicks based on the largest error region per sample object during training. The refinement click simulation is the same as in the validation and evaluation script of the challenge. And to supervise the model's prediction, we use a linear combination of focal loss and dice loss for the mask prediction with a weighting ratio of 20 to 1. If there are multiple objects in an input image, we apply non-overlapping constraints on the output mask lodges as a post-processing step. This ensures that in the event of potential mask overlaps, the selected label is not determined by the processing order, but rather by the model's confidence in the presence of each object. Here we can see the performance of iMedSTAM, our model, compared to the baseline models on the validation set. In addition to the 4 metrics relevant for the challenge, we also show DSC1 on the far right, which denotes the score obtained using only the initial prompt. As we can see, our model significantly outperforms SUMMET3D, Vista 3D, and SegVol on all 5 metrics, and is on par with the recent NN Interactive model. However, on the final test set, we saw that the NN Interactive model has a significantly better performance than our model. Reasons for that could be a different modality distribution in the test set, or that NN Interactive is simply better at generalizing. If we look at the results broken down by image modality, we can see that NN Interactive is very good at CT and PET segmentation, while iMedSTAM is the best model for MRI scans and ultrasound. And for microscopy, we can see that NN Interactive and Vista 3D are roughly on the same level. Vista 3D more for the metrics of NSD and NNN active more on the DSD values. Here we can see the interactive segmentation performance on the validation set with respect to the number of correction clicks. For all models, segmentation accuracy improves incrementally with each additional correction click. The only exception is SegWall, which processes only boxes as input and therefore cannot benefit from the correction clicks. iMedSTAM, here the blue line, performs especially well with just one or two prompts, but then is surpassed by NN Interactive, the yellow line, when more correction clicks are added. So NN Interactive really gets the interactive part. Here we have a CT example that iMedSTAM handles very well. In the upper row is the ground truth, and below is the corresponding prediction of our model. As we can see, iMedSTAM accurately segments and differentiates various abdominal origins throughout the entire volume. As seen in the middle slice, the model handles the segmentation of the light green liver, even when it consists of several separate regions in the plane. So that is not a problem. Here we have a challenging MRI example. As we can see in the 3D views on the right side, the model significantly oversegments the brown-colored tumor. Potential reasons could be that in this case, we only got the initially a point prompt and no box prompt, so it's a lot more difficult to catch these edge slices. And also, the input image has had a really low resolution, so that could lead to blurry object boundaries if we resize it. Yeah, limitations in future work. Similar to most of the other models, we had difficulties with the microscopy modality. This could be because it's a modality where we had really not that much training data. And we also experienced difficulties with 3D images, which have really large physical spacing between the slices, because that could lead to location jumps of the objects from slice to slice that are more larger than you would usually have like in videos where the object is only jumping like 1 or 2 pixels from frame to frame. In a practical setting, that's not relevant for the challenge, but usually a future possibility would be to train and develop modality aware models. So we train a model for CT images, a model for MRI images. I think that would be in a real setting a good approach because the user normally knows what type of image he's analyzing. And for the challenge, we could expand the training data set similar to an interactive. And interactive is also not using like the default training set, and is also including additional public training data that would be possible for iMedSTAM as well. And as I explained earlier, we used the efficient TEM architecture, which is more efficient, but we get a performance hit from that. Another possibility would be to use default sum2 model that would probably get you better metrics, but you keep an eye on the runtime upper bound of 90 seconds per case. And we also could try to implement the caching of image embeddings throughout the iterations, so you get shorter inference times. Yeah, and we published our code at GitHub, so if you want to try iMedSTAM, you can check it out. If you have any questions or difficulties, just open a GitHub issue, and I'm happy to answer.